Hi, everyone. So the final topic in Chapter 13 is the Lewis definition of acids and bases. You'll recall that at the beginning of our study of acids and bases, I defined acids and bases via the Arrhenius and Bronsted-Lowry definitions. In Bronsted-Lowry, we were thinking about acids as proton donors and bases as proton acceptors. In the Lewis definition, which is the most broad and general definition, so that's a good thing to note that this is the broadest definition of acids and bases. We define an acid as an electron pair acceptor and a base as an electron pair donor. So an electron pair acceptor is kind of like being a proton donor. Instead of giving away something positive, it accepts something negative. And a base is an electron pair donor, which is kind of like being a proton acceptor. Instead of accepting something positive, it gives away something negative. So it's really useful to think about non-hydrogen acids in terms of this definition. And it explains why coordinate covalent complexes form. Because this idea of electron pair acceptance and electron pair donation is behind a type of bonding known as coordinate covalency. In coordinate covalency, both of the electrons in a bond originate from the same atom. So let's take an acid that you know, protons, and a base that you know, hydroxide, and think about them in terms of the Lewis definition. So when protons interact with hydroxide to make water, this is the classic neutralization reaction. The hydroxide functions as a donor of electron pairs. So look at all these juicy electron pairs on the oxygen. One of these gets donated to the proton to make a new bond, a new covalent bond between O and H to form the water molecule. In this sense, the base is acting as an electron pair donor, just as we said in the Lewis definition. The acid is functioning as an electron pair acceptor. Both of the electrons in the new covalent bond originate from that oxygen, making this a case of coordinate covalency. So you could have told me from Bronsted-Lowry which was the acid and the base in that example. But the Lewis definition you will find is very useful to identify non-hydrogen acids. Let's take as an example boron trifluoride. Boron trifluoride is an electron-deficient species. It has a sextet instead of an octet around the boron atom. So it's electron-deficient. It has an empty p orbital on boron. This can react with F-, which is a very electron-rich halide, to make a coordinate covalent complex, BF4-. And the way it does that is the base, the fluoride, is an electron pair donor. It donates its electrons to the empty, hungry p orbital on the boron. So the electron pair acceptor here is the acid. One big clue to problems like this is that Lewis bases are always going to have lone pair electrons that they can donate. Okay, so for example, this is very electron rich. It's a great Lewis base because it can donate one of its electron pairs to make this coordinate covalent complex. Commonly, we will see transition metals as Lewis acids. For example, zinc 2+ is a transition metal. Transition metals make wonderful Lewis acids because they have lots of empty d orbitals that are hungry for electron density. So this makes the metals really good electron pair acceptors or Lewis acids. Zinc can react with 4 NH3 molecules to make a coordinate covalent complex. So this is a tetrahedral complex where zinc is being coordinated by those 4 ammonia molecules. And these arrows represent coordinate covalent bonds where both of the electrons in the bond are coming from the nitrogen. So we can see these covalent bonds forming. And it has a charge on it from the charge on zinc. So in this example, nitrogen is donating its electron pair to zinc 4 times because this is happening with 4 ammonia molecules. So the NH3 is functioning as the base, and the zinc 2 plus is functioning as the Lewis acid. So you should be able to identify Lewis acids and bases, and you can always do so by tracing the flow of electrons and identifying the electron pair donor, which is always the Lewis base, and the electron pair acceptor, which is the Lewis acid. And with that, we are at the end of Chapter 13. Thank you for listening.